In this section, we're going to talk about analog input and output. So first, let's talk about what it means to have an analog signal versus a digital signal. Digital signals, the ones we know of, are either on or off. This is ones and zeros, quantized information. That means that it's either one or the other. It's nothing in between. Analog signals, conversely, are everywhere. They're continuous. They make none of those vertical jumps. They always run smoothly between values, and they can take on basically any value. So the reason why we care in embedded systems is a lot of our sensors are digital. Some of the sensors that we've already been working with, like buttons, are digital. They're either on or off. Other sensors might be things like the window and glass breakage detectors in home security systems, or those car detectors at stoplights and stuff like that. These are digital sensors. They give us a yes or no answer. But there's lots of things in our environment that are analog. Things like humidity and temperature and brightness. These are variances on a spectrum. These are things that are quantities to be measured, not just the presence or absence of something. So the systems we're dealing with are fundamentally digital. So we have to convert our analog signals to digital and vice versa. So if we have an analog signal like this and we want to convert it into a digital thing, we can do something really straightforward and say anything above this threshold we're going to take as a 1, anything below this threshold we're going to take as a 0. So in this case, we've got a threshold of 1.65 volts. We're using a 3.3 volt system. So dead in the middle is our threshold for quantization, right? This is where we want to say anything above this is a 1 and anything below it is a 0. And you can see that we miss a lot of the analog signal. Basically, all of this variance here, everything in these little triangle areas, all this kind of stuff. So we miss a lot of the fidelity of this analog signal. So what can we do? We can increase our resolution. We can say, I want to use 2 bits instead. So in between, we have our maximums and our minimums. We say, given my maximum and minimum, I'm going to take 2 bits, gives me 4 different values, so I'm going to develop 4 thresholds. The upper and lower thresholds are our maximum and minimum voltages, and the ones in between are the ones that fall somewhere in between. So a 0, 0 represents 0 volts, a 1, 1 represents 3.3 volts, and we've got thresholds in between. Now if we try to quantize this, we get something a little bit closer. With 2-bit quantization, 2-bit conversion, I get the general shape, and I can almost see my sine wave here. My error has gone down, but I'm still missing a lot of fidelity. You can see there's these big error areas, and I'm way off here, right? So this is not as good. So the higher the resolution, the more fidelity, the closer we can get to either reading or producing an analog signal. Now we've been looking at the quantization. There's also an aspect of this in time that allows us to see how much fidelity we get out of a signal. Let's look at a tool that'll show us how this works. So in this simulation, we've got a sine wave coming in, and we have our samples here. These red lines represent the samples, the times that our computer is looking at the signal as it's coming in, and we have what our read in value over here, right? So as I play with the frequency of the sample rate, you can see that it changes. So if I decrease the sample rate, it gets smaller and smaller, and we're still seeing the sine wave, but it's really chunky because we are having to interpolate between the sample points. Here I grab the top one, the next one I grab is very, very much lower, so it's here, and then the next one after that is at the bottom of the thing, so that we're jumping around quite a bit. And if I lower my sample rate enough, it starts to not look like a sine wave anymore, right? So here I'm just about the same frequency as I'm sampling at just about the same frequency as my sine wave, and you can see I'm out of phase. So here I'm right at 0. I skip a trough, I'm right at 0 again, and that shows in my samples here. Similarly, if I have different quantization values, if I use more detail, my sample rate, even if I'm using 12 or 13 bits, my sample rate has limited how much resolution I can get on the signal itself, because I'm not getting in there and getting all those things, getting all the detail in the signal. This is what's called the Nyquist limit, and the idea here is that to accurately capture the frequency of a signal, I have to read that sample at least 2 times the frequency. That way I get a peak, and then again I get a trough. So because I want to make sure that I'm not sampling on the same frequency, because I could end up just being on zeros all the way through. If I'm sampling at 2 times the frequency of my input signal, then I know I'll get my 0, I'll get a peak, I'll get a 0, I'll get a trough, and that gives me at least most of it. So the minimum here is if I want to sample a 60 hertz signal, I have to sample it at 120 hertz. So the next 2 videos are going to look at the input and output sides, the specifics of how we actually implement digital to analog and analog to digital conversion.